In the previous lesson, we learned that a set can be given a name. This is helpful as we don't have to keep rewriting all the elements each time we make reference to the set. In this example, P is the name of the set. So P is the name of the set. And set P contains all even numbers greater than 2. So to our right hand side, this is the description we should also note that each item in this collection is called an element. It should be noted that I arbitrarily chose a name for the set. I could easily say this set is called E, or I could say it's called K. However, in mathematics, some sets are so significant and prevalent that we reserve special names for them rather than just arbitrarily naming them. We will now have a look at some of these sets. The first one is a set of natural numbers. Natural numbers are used for counting. These include 1, 2, 3, 4, etc. The set of natural numbers is denoted by the letter N. It's a capital N. So the set of natural numbers is equal to 1, 2, 3, etc. The next set is the set of whole numbers. The set of whole numbers includes 0 along with all the natural numbers. The set of whole numbers is denoted by the letter W, and this is the uppercase. So the set of whole numbers is equal to 0, 1, 2, 3, etc. Note that the only difference between the set of whole numbers and the set of natural numbers is the presence of 0. If we continue to look at the set of whole numbers, we can see that the set of natural numbers is a subset of the set of whole numbers. We could even write the set of whole numbers as 0, n, where n is the set of natural numbers. So, the set of natural numbers is a subset of the set of whole numbers. Recall that set A is a subset of set B if the elements of set A are also elements of set B. The next set we are going to look at is the set of integers. Integers are whole numbers that are either positive or negative. Example, -2, -5, 0, 1, 7. These are all integers. The set of integers is denoted by the letter Z, and of course this is a capital Z. So we could do set notation, so that is -3, -2, -1, 0, 1, 2, 3, and so forth. Remember that the dots at either side mean that it goes all the way to -infinity and positive infinity. Now, if we look at the set of integers, we can see that the set of natural numbers and the set of whole numbers are also a subset of the set of integers. So we can write the set of natural numbers is a subset of the set of whole numbers, while the set of whole numbers is a subset of the set of integers. These are very important points. The next set we are going to look at is the set of rational numbers. Rational numbers came about out of the need to quantify and sell quantities that were fractional. Rational numbers are made up of ratios whose decimal either terminates or repeat. For example, 1 divided by 3 is a rational number that's equal to 0.33333, and it repeats. 3 over 8 is also a rational number, and that's equal to 0.375. and this is a terminating decimal. We should also note that the set of integers can be written as ratios with denominator 1. Example, 5 is equal to 5 over 1, minus 7 is equal to minus 7 over 1, 0 is equal to 0 over 1. We normally denote the set of rational numbers using the letter Q, that's uppercase. We will see how we can use set builder notation to represent the set of rational numbers. Now, if we were to continue our subset train, we can see that the set of natural numbers is a subset set of whole numbers. The set of whole numbers is a subset of the set of integers, and the set of integers is a subset of the set of rational numbers. The next set we will look at is the set of irrational numbers. An irrational number is any number that cannot be fully written as a decimal or ratio. The decimal part neither repeats nor terminates. A perfect example of irrational numbers are surds. A surd is a number whose square root cannot be simplified. For example, root 3. And this is equal to 1.7320508808, etc. The decimal portion of this number does not repeat. It neither terminates. Root 2 is also a surd. Root 4 is not a surd. Why? Because root 4 can be simplified. So if we simplify root 4, we get plus or minus 2. And this is an integer. We will denote the set of irrational numbers by Q star. The next set we will look at is the set of real numbers. Real numbers are very important because we will be working with real numbers for majority of this course. So what is a set of real numbers? So combining the set of rational numbers and the set of irrational numbers creates the set of real numbers. And we denote the set of real numbers by R. That's a capital R. And this is equal to Q, which is the set of rational numbers, and Q star, which is the set of irrational numbers. So what's next? We could go further and identify a set called the set of complex numbers. The set of complex numbers are roots of negative numbers. For instance, root of minus 2 is a complex number. The root of minus 3 is a complex number. The root of minus 5 is a complex number. Now, when we look at complex numbers, we will see that a complex number is normally denoted in such a form: AI plus B, where A and B are real numbers. So A and B are elements of the real number system, and I is an element of the set of complex numbers. We normally denote the set of complex numbers by C, capital C. I should also mention that I is equal to the root of minus 1. If we were to type minus 1, the square root of minus 1 in our calculators, we get a math error. So our calculators are programmed to only deal with real numbers. We will discuss how we can deal with complex numbers in the later chapters.